So, what did you get?
Lots of stuff.
I thought Mikhail was with you on the journey, man.
He was, but I'll tell you about that later. For now, we have to focus on the elephant in the room.
Okay,
Our team has found another fat.
what kind? Is it GAA fat?
No, CNTFET. So, CNTFETs use carbon nanotubes as the channel material instead of silicon. And carbon nanotubes have some unique properties like high electrical conductivity and mechanical strength, which makes them promising for next generation transistors. They also can potentially offer high performance, better speeds, and also better scalability compared to traditional FETs. And my team are able to shrink ourselves down to the CNTFET, so we were able to get inside the CNTFET.
Fascinating. The history of CNTFETs can be traced back to the discovery of carbon nanotubes themselves. Carbon nanotubes were first observed in 1991 by a Japanese researcher named Sumio Ijima. Within just 7 years, a team led by Chees Dekker at Delft University of Technology in Netherlands demonstrated the first carbon nanotube, or CNTFET. This was a game-changing breakthrough as it showed that carbon nanotubes could be used as the channel material in a transistor with properties that could potentially outperform traditional silicon-based FET. So, did you get the FET?
Where are we?
CNTFET.
Yeah, I know, but where specifically?
I think it's we're on the drain, I think.
I don't even know how fat works, so I don't understand where we are, bro.
Let me explain.
Really, bro?
Yeah, that's I'm being honest, bro.
It is a bottle.
What?
And what?
Imagine holding a bottle. And you squeeze it. And a straw penetrates its cap. The squeeze bottle represents the source of the electrode, where liquid flow starts. When you squeeze the bottle, liquid flows into the straw, and the straw represents the carbon nanotube channel. It is made of a unique, smooth material that lets liquid flow quickly and easily. This is similar to the high carrier mobility in a CNTFET, where your finger acts as the gate electrode. By partially covering the top of the straw, you can control the liquid flow inside the straw, and which it deflects the flow rate from the bottle source to the opening, which is the drain of the CNTFET. The opening at the top of the straw represents the drain electrode, where liquid flow currents exist. The flow rate depends on how hard you squeeze the bottle. Just as the drain voltage can influence the current flow in the CNTFET. A small piece of plastic wrapped between your finger is the gate, and the top of the straw CNT channel represents the gate dielectric. This keeps the insulating layers keeps your finger from directly touching the straw while still allowing your finger's pressure to influence the liquid flow through the straw.
So we're at the tip then? If we're at the drain side, then where's all the electricity?
Unfortunately, I cannot answer that question because I'm too can't figure out what's going on. Therefore, let's just go to the drain source.
Okay, to the bottle it is.
The journey begins as we explore. We see the carbon nanotubes. And finally, the source. Still don't understand why the electrics are gone. Like, you guys could have died.
We found the problem. It was at in Bob lab.
Is this looking intriguing?
We're finally at the drain, and that is the drain. The source of the problem.
It looks like it's been turned off.
Intentionally, we need to turn it on.
But who turned this off? Who is crazy enough to turn this off? Because, for one, they have high career mobility, which allows for faster and more efficient electronic devices. They also exhibit ballistic transport, which results in lower power consumption and also higher efficiency. Their mechanical flexibility makes them great for flexible and wearable electronics too. And then they also have excellent scaling potential, enabling further miniaturization of electronic devices. And let's not forget that their superior thermal properties, which can help with heat dissipation and improve overall performance and reliability. All these advantages make CNTFETs an incredibly promising technology for the future of electronics.
I won't do that if I were you.
Erdi?
Hello, old friend.
What? He was an agent before you.
Well, surprise!
I thought you were dead. What happened to you?
You abandoned me. That's what happened. Right where you left me. I started to stumble on the source into the drain.
Oh god, he's absorbing all the electricity.
That's why the electricity was off all along.
I need to do what I need to do. You are gonna destroy this place.
I have told you! The disadvantage of this technology, fabricating them is complex, especially when it comes to aligning the nanotubes and controlling their properties. Additionally, purifying the mixture of metallic and semiconducting nanotubes is quite difficult. It's also challenging to establish low-resistant contacts between nanotubes and metal electrodes, and integrating CNTFETs with existing silicon technology is no easy task. There are also concerns about the potential environmental and health impacts of carbon nanotubes, as well as the long-term stability and reliability of CNTFETs.
It can help humanity thrives. You need to understand that.
You killed me before, and now you're dead.
Wait, so he's gone?
Rest in peace, Miguel.
Rest in peace, man. Erdi was wrong. The potential of CNTFET is a lot. Because CNTFET have a lot of potential uses because they offer unique advantage over traditional transistors. Some of this application include faster and more efficient electronics, flexible and wearable devices, high-frequency communication system, energy-efficient, low-power devices, bioelectronics, and medical devices, and even space resistant to radiation. As research progresses, we can look forward to discovering even more exciting applications for this promising technology.
I know. I needed to turn on the source again. Then I tried to fight him over and over again.
You think you can save this planet with a FET?
But then I succeeded, and despite the challenges and disadvantages associated with the development, ongoing research is actively addressing these issues. And as we continue to make progress in understanding and harnessing the potential of CNTFETs, we can expect them to play an increasingly important role in shaping the future of our technology and also enabling innovative new devices.
Nice one, nice one. Well, then hurry up then. We need to make a funeral for him.